Look at an old church window, and you'll sometimes notice something strange. The glass is thicker at the bottom than at the top. For decades, that little detail spawned one of the most persistent myths in casual science conversation, the idea that glass is secretly a liquid and that over centuries it slowly flows downward like impossibly slow honey. It's a compelling story. It's also mostly wrong. At room temperature, glass is not creeping down a window pane. It is not dripping, not sagging, not migrating molecule by molecule toward the floor. Glass is an amorphous solid, and understanding what that phrase actually means is where the real story gets interesting. Start with what glass is not. A crystal, like salt, quartz, or a metal, is built from atoms locked into a neat, repeating, geometric pattern. Zoom into a grain of table salt, and you would find the same tidy lattice arrangement expanding outward in every direction. Glass never does that. When molten glass cools, its atoms don't have time to organize themselves into that repeating structure. They get frozen in place while still tangled in the disordered arrangement they had as a liquid. The result is a material that is rigid and solid. You can drop it, stack it, lean a ladder against it, but internally, it looks structurally like a liquid that got stuck mid-thought. So, if glass isn't flowing, why are those old windows thicker at the bottom? The answer has nothing to do with physics happening after installation, and everything to do with how the glass was made in the first place. Medieval and early modern glassmakers didn't have the precision tools we have now. Their techniques, spinning molten glass into discs, or blowing and flattening cylinders, routinely produced panes that were uneven from the start, with wavy surfaces, trapped bubbles, and edges that varied in thickness from one side to the other. When builders cut these imperfect sheets into panes and installed them, they often placed the heavier, thicker edge at the bottom. It made intuitive sense. A pane feels more stable and less likely to pop out of its frame when the weight sits low. That was a construction choice, made once, at the moment of installation. It had nothing to do with centuries of gradual sagging afterward. Over time, as people noticed this pattern across many old buildings, they reached for an explanation, and the idea that glass secretly flows very slowly was an appealing one. It fit the visual evidence, and it sounded like the kind of counterintuitive fact that feels true. But the manufacturing explanation fits the evidence just as well, and it doesn't require inventing physics that isn't happening. That's usually where good myth-busting starts. Not just showing that a story is wrong, but showing what much more mundane explanation was sitting there the whole time. None of this makes glass boring, though. It makes it stranger. True liquids that get frozen without crystallizing are actually rare and scientifically important. Glass begins its life as a hot liquid, exactly like the old myth assumes. But then, instead of forming an orderly crystal lattice as it cools, the way water freezes into the repeating structure of ice, glass's atoms get stuck. They run out of energy before they can find their way into a tidy arrangement. What's left behind is disorder that has been locked in place, frozen chaos rather than frozen order. That frozen disorder is exactly what gives glass its unusual mix of properties. It's transparent, because it lacks the crystal boundaries that scatter light in most solid materials. It's brittle, because it has no repeating planes along which it can bend or deform gradually, the way metals do. And it's smooth, because without crystal facets, its surface doesn't have to follow rigid geometric angles. This in-between nature is exactly why scientists still study something called the glass transition, the process by which a liquid becomes a rigid, amorphous solid without ever crystallizing. It's a genuinely active area of materials science, because glass doesn't fit neatly into liquid or solid as those categories are normally defined. It forces scientists to ask harder questions about what solidity actually requires at the atomic level. So the next time someone tells you, "Old windows prove that glass flows," you can set the record straight. It's not gravity dragging glass toward the floor over centuries. It's an old manufacturing quirk, misread as physics. But the real explanation is more interesting than the myth. Glass is a liquid structure, frozen mid-motion, clear enough to see through, and strange enough to keep scientists asking questions generations later. Follow for more random things you may not know.